let's put all this together, and then from our atomic orbitals of beryllium and our salx from the two hydrogen atoms, let's generate a molecular orbital diagram, okay? And so, as we talked about, as we are used to think about with the diatomics, right, we had one atom from the diatomic molecule on one end of the MO diagram and the other atom over here. But we're doing something different here because we have a triatomic, right? And so what we're saying is that on one end we have the central atom, in that case that's beryllium, okay? And then we have the orbitals, the energies of the orbitals that are our basis set for beryllium over here. We have the 2s and the 2p. And then on the other side, right, we have the salx that we generated, okay? And we have our 1s plus 1s HB, HA minus 1s HB. Okay, so again, or anti within the salx. Those atomic orbitals are not interacting with each other, and so those salx are, we consider those degenerate. Another thing you'll notice, right, and this should make some sense from our discussion of heterodiatomic MOs, right, is that the energy, right, for the salx are much lower than energy for the corresponding 2s and 2p orbitals from beryllium. And that makes sense, again, because we expect that those energies for a 1s orbital to be much lower than that for a 2s orbital. And so that means that the salx, right, again, because they're not interacting, the atomic orbitals that make up the salx are not interacting within the salk, right, they're going to have the same energy as the 1s orbitals of hydrogen. So these are going to be much lower in energy than the 2s and the 2p orbitals of beryllium, okay? So from there, right, our lowest energy orbital are going to be derived from the 1s beryllium, but we're going to not pay attention. We're going to ignore those. So we're just paying attention to our basis set here, right? And so we have our the first orbital that we're going to have is going to result from interaction between the 2s orbital and the 1s HA plus 1s HB. So that formed the sigma bonding orbital that we described in the previous video, okay? And that's going to be our lowest energy orbital, and we're actually going to call that 2 sigma because there's a sigma bonding orbital below this, right? All right, so the next one, right, is going to be our next sigma bonding orbital, okay? So our next bonding orbital, and that's going to be this that's derived from, and before I get there, so remember that this is derived from the 2s orbital of beryllium, and then the 1s HA plus 1s HB, okay? The second bonding orbital we were able to make from combination of beryllium atomic orbital and a salk is this sigma bonding orbital, which is a result of overlapping, right, the 1s HA minus 1s HB salk, and then the 2pz orbital, okay? And so you'll notice, okay, this is, again, this is slightly lower in energy than the, this is slightly lower in energy than the energy of the orbitals it's derived from, okay? The salk in this case, all right? Okay, and then we have a mark that goes like this, okay? Because it's derived from the 2pz, all right? Now remember those px and py orbitals that didn't overlap with anything. We couldn't find a salk to overlap with, okay? They have no combination with any of the salks, right? And so there's no way to decrease their energy. So what these end up being are, we have the px and the py orbitals, all right? And these are non-bonding, okay? So they're not bonding with, these orbitals are not bonding with the hydrogen atoms, and they remain at the same energy as the atomic orbitals that they're derived from, okay? And then from there, we're going to place the anti-bonding orbitals that we generated. So turns out in this case, right, the next one is going to be 1 sigma star, right, which is actually the combination of the 1s HA minus 1s HB and the 2s orbital, okay, so that's this one up here. Okay, and then we have the 2 sigma star, which is this antibonding orbital here. All right. And notice that all the bonding orbitals, again, are slightly lower in energy than the orbitals that that they were generated from. The antibonding orbitals are all greater in energy than the orbitals the atomic orbitals and salks that they were generated from. Okay, and so this is our molecular diagram for this MO diagram. Right, the electron configuration for beryllium was 1s2s, so we just have the 2s electrons here because we're not considering the 1s orbital. And then there was 1 hydrogen atom from each, or 1 electron from each hydrogen atom. So we have this, and so we're going to fill up 4 electrons. Okay, and so our MO diagram along with the electron configuration shows that our highest occupied molecular orbital is the 3 sigma, which, if you remember, will be this one. This is 2 sigma. Okay, and then our LUMO will be the non-bonding orbitals that look exactly like the px and py orbitals for beryllium.